Welcome to the Agilent ICP-MS introduction video. Today we're going to talk about our Agilent 7500 CE inductively coupled plasma mass spectrometer, or ICP-MS. We're going to do a quick overview of how the system works, not going into a crazy amount of detail, and then we'll do a hardware overview video. We're kind of going to ignore the sample introduction part of the system because it's very complex and there's a lot of different options out there. So there's laser ablation and liquids introduction, so for solids or liquid samples, but there's also different types of liquid introduction like organics or things with HF that require inert things or things with high total dissolved solids. So we're just going to kind of skip this number 2 section on the diagram here. So this is kind of a cross-sectioned cartoony diagram of our instrument. And so either the liquids or the laser mode are both going to give us a very fine mist, or I guess dust ablated product that will enter the plasma. So the plasma is generated by an RF frequency. I think it's 27 megahertz RF frequency that's passed through a coil around the torch. So the argon flows in, and the coil, the RF frequency causes the argon to collide with itself with such energy that it generates the plasma after it, so it ionizes and causes a chain reaction of ionization that causes it to generate the plasma. And so the torch is made of quartz because it needs to be very temperature resistant. Obviously, this plasma is very hot. The very center of the plasma is somewhere around 7 to 10,000 degrees Kelvin, and the outer parts are definitely cooler, but still quite hot. So once the sample has entered the plasma, it should be fully ionized. Now that is the ideal case. So what we actually have when we, after the sample enters the plasma, is monoatomic ions, which would be the ideal things that we're measuring because we only want to know the mass of the individual ions. We'll have polyatomic ions, also known as interferences, which might be measured as an incorrect mass. So this might give you erroneous data. And then we should have some neutrals and things that might have been quenched. This might not happen until just after the plasma, but we can kind of consider all three things present at the same time. And then there is a fourth thing, which is photons. So the plasma generates a lot of light, and we don't want those to get to our detector either, but that is a much easier thing to deal with. So the first thing that this ion stream or sample stream encounters after the plasma is the sampling cone. So this is a nickel cone, and you'll be able to see this towards the end of the video up close. But this is a cone that the plasma hits directly, and it's water cooled, so it doesn't melt or anything. But it has a tiny orifice that's 1 millimeter wide. So this is just a little hole, and you line it up so that the hottest part of the plasma is hitting that hole, so it'll go through it. And behind this cone, there's a vacuum. So the ion or the sample stream will actually be sucked into the hole as well as just being shoved in there by the force of the plasma. And the purpose of this cone is to skim off, why it's called a skimmer cone, is to skim off all the excess stuff. So anywhere that's not the hottest part of the plasma has a much higher likelihood of having these undesirable things such as neutral species and polyatomic ions. And there's other things as well, but these are the basic things that we worry about. And so once we go through this first cone, we're now in vacuum, and there's actually a second cone directly behind it called the sampling cone that has a smaller orifice of 0.5 millimeter wide. And so this skims off even more stuff that we don't want going into our detector. And then right behind that are a set of electromagnetic lenses. And these lenses are going to focus and accelerate the ion beam. And then there's the very last lens is our vertical deflection lens, which actually takes the ion stream and diverts it a few millimeters up. And then anything that's not diverted, such as neutrals or photons, because those don't interact with the electromagnetic fields of the lenses, those will directly hit a plate at the very end and be sucked into vacuum or deposited onto the plate. And then they won't be present in the stream anymore. So we've effectively removed 2 of our 4 items right there. Now the ion stream will enter the octopole reaction system. So the octopole has 8 poles, as the name implies, and all it does is try and keep the ion stream focused and going in the right direction. But we still have monoatomic and polyatomic ions in our stream. So we use the reaction cell by filling it with helium gas. And so the helium gas the ion stream will collide with the helium gas. And the polyatomic ions are much, much larger than the monoatomic ions, and therefore they will collide thousands of times more than the monoatomic ions. So everything is colliding with the helium, but the monoatomic ions are colliding so much less that the amount of them that are knocked out of the ion stream are going to be much, much lower. And so we are going to lose signal all around, but the polyatomic ions will drop so low as to only be a fraction of what they started out as. And so anything that collides has the chance of either losing momentum or being knocked completely out of the ion stream and sucked into vacuum. And so this is how we're going to remove those interferences, by having them get knocked out of the ion stream. And if they lose enough momentum, we actually apply a plate bias to the exit of the octopole. And so if enough momentum is lost, they might be repelled and not even make it out of the cell. And that's another way that we filter those out. And so after going through the octopole, we should only have monoatomic ions left, and then they will enter the quadrupole. The quadrupole, as the name implies, has 4 poles, and it uses a combination of radio frequency and DC voltage to act as a mass filter. So this thing can scan these voltages and it can eject every mass except one that it's looking at. So if, for example, you wanted to measure mass 56 for iron, then it would set to its preset voltage for iron 56, and then everything but 56 gets ejected into the vacuum, and only 56 will make it to the detector. And so we do this, we scan through all the ions or all the masses that we're interested in and count each one individually. And this can happen very quickly, so the system can scan through all 200 masses in less than a couple seconds if needed. But usually we do longer integration times so that we get higher counts and better signal to noise resolution. And so the detector is just an electron multiplier at the end. So the ions hit the multiplier and generate electrons, and those electrons cascade down the diodes and amplify the signal. And that's where the counts come from. So that was the basic background behind the ICP. So now we're going to look at some of the hardware. Let's take a look at some of the hardware used for the ICP-MS and how we're going to operate this thing. So we start with our computer operating area, which has 2 different computers. So those 3 screens are split between 2 computers. One computer operates the laser ablation system, and one computer operates the ICP-MS. So let's first take a look at the laser ablation system. So this is a New Wave Research UP213 neodymium YAG laser. So it's 213 nanometer deep UV laser. So this thing uses a helium carrier gas. So our cell is located down here, and It's a little hard to see, but right in here is where we put our sample holder. So here's the sample holder that we're going to look at, and it simply inserts into the cell here and then clamps down to form a tight fit. The laser then will ablate the sample. Helium enters the cell in the back, exits out the side, and then is carried over into the argon plasma. So that's our introduction option for solid samples. And then we have an introduction option for liquid samples. So this is our auto sampler for the liquid portion of ICP-MS. It has a 21 rack sample holder for 50 milliliter samples. And then it has 360 slot racks for 15 milliliter centrifuge tubes. The bottles in the back here are rinse bottles / standards. So those are used for rinsing the probe. So the probe is located here, and the probe is what goes down and dips into each standard and each sample, and then it is rinsed through water at the home port here, as well as the different rinse bottles there. Okay. The pump that pumps the liquid is over here. It's not currently set up, but this is a peristaltic pump, and it pumps the sample from the probe all the way into the plasma. So, or all the way into the spray chamber. So it pumps the liquid into the nebulizer here. So here's the nebulizer, where it combines it with argon and sprays it into a very fine mist. And then it proceeds to the mist and the argon. The argon carries the mist, through the spray chamber. So the spray chamber has a long path for the liquid droplets to flow before they go towards the plasma. And the spray chamber is cooled down to promote condensation of larger droplets so that they won't make it into the plasma where they could cool it down and cause incomplete ionization. And then in here is where the plasma torch is located. So the mist, the fine mist of liquid droplets, will go into this quartz tube. And then I've already loosened up this cover. So it'll go through the quartz tube into the torch, and the torch takes two different argon streams. And there we go, into the quartz torch. And the coil right here applies the strong RF signal, which generates the plasma. So the plasma is an argon plasma. This uses around 20 liters a minute of argon gas. And so your sample stream, whether it be from the laser using the helium carrier gas to carry the sample, or from the liquids where it nebulizes it into a fine mist and then is carried by argon into the plasma torch, they're all ionized. And then it goes here into the sampling cone, which is the interface to the vacuum. So we can't actually look inside the vacuum chamber because we don't want to open that up. First of all, venting it takes a long time, and pumping it out again, but you don't want to open vacuum systems unless you absolutely have to. But we can look under the cover here a bit and get an idea of the layout. So let me refocus my lens. So this part here is the vacuum chamber. It's pumped out with a split port turbo molecular pump that's located underneath. You might be able to hear the whining from it. I don't know if my headset can pick that up or not. On the back, this red part here, that's the pressure gauge. And then on the front here, we have the electronics, and on the back side here, these are for the detector system. And then the rest of the stuff in the back here is more electronics and power supplies and control modules and stuff like that. And so the system, as I mentioned, uses a lot of argon. So on the end, we have a dual argon manifold. So this manifold allows us to hook up two different argon tanks so that we will never run out of argon during a run. The system also requires a water chiller to cool down the cone that the plasma is directly hitting, as well as to help cool down the Peltier device that is cooling the spray chamber down. We also have a couple different gases in the back. So we have a helium tank that is specifically for the laser ablation system. So that's the carrier gas there. And then we have another helium tank that is the octopole reaction gas, as well as another optional octopole reaction gas of a hydrogen tank down below. Overall, this system operates very well and gives us really good sensitivities. For most elements in liquid mode, we can get into the low to mid parts per trillion detection limits. And for the laser ablation system, we can usually get low part per billion detection limits on most of the elements. So let's take a look at a few of the different parts that I showed you just now, but we have some old, used, or broken versions that we can show you a lot closer. So the first thing that we can show you is the quartz torch. This is the plasma torch. Okay, so here's the two ports where the argon was input, and you can see that the way it comes in, they kind of form a little vortex, so they come in at an angle, so they're going to cause a swirling motion, which will help confine the hottest part to the center. So there's two different ports there. The sample stream comes in here in the center, so there's three concentric tubes in there, and the sample stream comes in the center, whether carried by helium or by argon. And then the coil was wrapped around the end of the torch here, where the plasma is generated. Okay, the plasma was then running up against the sampling cone, skimmer cone. So this definitely looks tarnished because it's old and has been handled a lot. But this part here is all copper, so it's solid copper. It's normally pretty shiny on newer cones. And then the part in the middle here is nickel, and nickel can handle really high temperatures, so it's a good choice for this. The whole copper plate, the purpose of the copper plate is to keep everything cool, so this is cooled by the water chiller that I mentioned, and so the nickel won't melt under the full heat of the argon plasma. The tiny interface hole there is supposed to be 1 millimeter, and we have to make sure it stays very round and doesn't get deformed. So we don't really handle these cones unless we have to for cleaning or maintenance or changing them out. And the whole point of the tiny hole is to give us an interface between the vacuum as well as skim off any excess of the sample stream that we don't want, which might be colder or full of polyatomics or interferences or things like that. Then directly behind that cone is this skimmer cone, so it's also made of nickel, but again, it's tarnished, and it screws into this lens stack here. So this one has an even smaller orifice. I think it's 0.5 millimeter, and it's much more fragile. So again, with ones that are in use, we really don't try and handle them except for maintenance and cleaning. And then this is a lens stack. So this is an old lens stack, which is actually missing the deflector. So I don't have one that I can show you that has the deflector on it. But you can see the lens stack here with all the insulators between the different lenses where they attach. And that's so that each lens can have different voltage applied. So they're all, there's little pins that touch each lens in a different spot and apply voltages. So there's focusing and accelerating lenses here, but in the real lens that's in use, there's a plate over the back with a hole in it that's offset by a couple millimeters from the main orifice, and that is to deflect the ion beam. And then immediately after the lenses is the octopole. So somehow we have a broken octopole. I have no idea how you break one, but they are not something you want to be handling very often. But the octopole is just what it sounds. It's got 8 poles, and they are nominally all parallel to each other and equally spaced around a central axis, but these are off kilter quite a bit. And this whole cell is sealed, so you can see there's O-rings on the ends here. And this is what we pump with different gases, so either helium or hydrogen, depending on if we're going to do collision mode or reaction mode. Okay. And then it goes to the quadrupole, which we don't have one of those to show. But the quadrupole is our mass filter, which filters out everything to a single M/Z ratio. And then this is an electron multiplier that does the counting. So you can see from the top all the different dinodes. And then this is the hole where the initial ion comes in and strikes. There's a different colored plate there, and that's the one that the ion strikes and generates electrons, and then they cascade down for amplification down the different plates there. Okay, all these little springy looking things, those are the different electrical contacts, as well as this one on top, which is a screw type coax attachment. So this is where the counting is done of the ions and gives us our actual data. So electron multipliers have a finite lifetime, and so this one actually just outlived its time and had to be replaced. But it's nice that we can show it to you. It looks a little different than some electron multipliers you might see, which are more of that cornucopia shaped one that does the little spiral.